but this is based on a course I teach every fall.
So if you want to read about these ideas of dynamic networks, I recommend actually some good Wikipedia articles. There's a handout, which actually we should distribute, maybe Maciek. There's a cheat sheet there on Tellurium. Could you hand that out? Andy, maybe you could hand that out, please. It's printed there. These lectures are mostly based on some textbook by Herbert Sauro, and all of those are actually available online for Herbert's website. I'm going to assume that everyone has Tellurium running. I know that the Spider wasn't working on Macs, and so people who have a Mac should open whatever the IDE for Python that they were using was. It's critical that you have your computer. If you don't have your computer running, this is going to be a very long afternoon. So it's really important that people have their computer running. And so we're going to be talking, so far we've heard a lot about how to do modeling of cell behaviors and cell interactions. And Julio this morning was talking about subcell compartments and how to manipulate them. What we haven't really talked about so far is how cells make decisions at a molecular level. And so when we talk about network modeling, typically we're going to be talking about what's going on inside of cells and how cells are making decisions. Big questions, and this will come up actually when, the reason I wanted to do this now is because Furkan will show decisions that cells make in terms of differentiation, changing cell behaviors. Cells send and receive signals in a variety of ways. We've seen simulations in which we had diffusible chemicals. We've seen simulations in which we have contact between cells. There are other ways cells can signal as well. And so those are really the kinds of questions we're going to ask. And if we had a semester to cover this material, we would we'd go into more detail about the mathematics of it. When we come to thinking about biological networks, and we want to talk about networks that actually represent molecular species per se, we find that there are 4 kinds of networks that we'll run into, what are typically called chemical reaction networks or sometimes metabolic networks, which destroy or create the components of cells. Signaling networks that transfer information within and between cells. Regulatory networks that turn genes on and off. And then a non-cellular kind of network, which is used a lot in industry, which is called physiologically based pharmacokinetic models. And in these, the model is actually of transport of molecular species within the body. And you might say those look very different from these molecular networks, but mathematically they have identical structure. And so treating them in the same way makes sense. There also are some additional kinds of network structures that we run into quite a bit, one of which would be what we would call population dynamics models. That is, you say that, for example, you have n cells of a given kind, and you have a model, a non-spatial model of how those populations of cells change. Lots of cancer models work that way, lots of ecosystem models work that way. A certain number of developmental models of, for example, leukemia almost always are built that way. And the last one would be called, doesn't really have a name in general. You could call them perhaps outcome networks. If you're a toxicologist, they're called adverse outcome pathways. And this is something we're going to face actually in all of the models we build, which is, as I've mentioned before, if you have a molecular signaling network that gives you a molecular concentration, you need somehow to connect that molecular concentration to some behavior of the cell. And that means making some phenomenological assumption about how those things relate. And instead of being afraid of that, it's something that we simply have to embrace. There is no simple relationship between a molecular concentration and a cell behavior, because cells can have identical molecular compositions and be totally different in their behaviors. You could have two cells that if you did mass spec were identical, but they're completely different. So molecular concentration by itself isn't sufficient to specify cell behavior. Toxicologists are used to that because, for example, they'll say, well, you expose the person to arsenic. That has effects on proliferation of cells in the liver. It might have effects on kidney function. And so you'll have input-output relationships, which usually are characterized as sigmoids, but these can be quite abstract. The health of the system could be an output. And so we have to think about ways of representing that. Okay. Just as a tiny bit of background, a network, by definition, is a model, and it has two kinds of things in it. It has nodes, which are usually dots, and links, which are usually represented by lines. And there are going to be all sorts of different nodes and links models, but we're going to be focusing on ways of modeling not the topology of networks or their structure, but rather on how, for particular identities of nodes and links, the values at links and nodes change. And it's worth saying, and I said this before, that a network model is intrinsically not a spatial model. It intrinsically lives in an abstract world. It doesn't live in real space. We can certainly embed it in real space, and we'll do that. But it by itself is not a spatial model. And that's going to have some consequences for how we understand these things. So in a dynamic network model, the links are going to represent some kind of interaction between the nodes. And by an interaction, we mean that there's going to be a change of the state of the nodes due to that interaction. And typically, when that is the case, we will represent those links not by straight lines, but by arrows. And one of the things that we're going to have to face, yes, so that's actually something we'll talk about. The answer is that if you represent A, B, and C explicitly, and the only connection between A and C is via B, then you represent it that way. One question that you run into a lot is whether you can simplify the mathematical representation of something by getting rid of the intermediate components. And sometimes... So the question, so let's defer that. The only thing I wanted to say about this slide was simply that you'll see lots of arrows, and you'll discover that as you look at different papers, different articles, that the usage of arrows is not consistent. And so you have to live with that. Okay. But in general, when we're talking about a dynamic network, we're always going to have the concept of nodes, and these nodes typically have states associated with them. And for a biochemical network, those states would be either the amount or concentration of a particular chemical. The links are going to define how the values at the nodes change. And so what a link represents is a rate law, a rule about how values change. And again, this may sound very abstract, but in fact, it's worth going over the abstraction at least a little bit, because we're going to be using it again and again. We're going to see it again and again. All of the examples I give have the same mathematical form. Okay, so we're going to talk about a chemical reaction. People are probably used to seeing things like a chemical reaction formula. Here, 2 molecules of ADP go to 1 molecule of ATP, and 1 molecule of AMP. So 2 adenosine diphosphates go to an adenosine triphosphate and adenosine monophosphate. That happens to be a reversible chemical reaction, and so the arrow is usually drawn with 2 heads. We could also have some more complicated cascade of reactions. 2 molecules of A go reversibly to B, molecule of B goes reversibly to 3 molecules of C, and a molecule of C plus and a molecule of A can react to form a molecule of D. Chemical reactions conserve mass. Most of the networks that we're going to worry about don't conserve mass. And if you look in the literature, a lot of, for example, Herbert's textbooks are devoted to understanding mass conservation. And if you're doing chemical reactions, that's great, but most of the time we won't be. And so, something to think about. Okay. There are, as I mentioned, a number of different conventions for how you represent these things. In this case, I've taken this set of chemical reaction formulae, and we've drawn them in the form of a diagram with arrows. And one question with arrows is to try to represent the fact that it's 2 molecules of A that make 1 of B or not. And some people use a convention where the number of tails of the arrow tells you how many copies you get. Obviously, if you have 27 of something going to 39 of something else, that's not a very practical way of drawing things. Okay. Fundamentally, what we're talking about, if we're talking about chemical reactions, is collisions between molecules that lead to changes of molecular state. And Tellurium, which is the software package we're going to be using and which we're going to connect to CompuCell, was initially conceived primarily for the point of view of modeling chemical reactions. Again, because the mathematical structure of all of the networks is the same, we're not restricted to that, but that's what we do. Okay. And so now let's think about a molecular reaction, simple as possible one. A and B react to make 1 molecule of C. Well, if we want to turn that diagram into something that we can simulate, the very first thing we need is that we need to know what the rate of that reaction is. Once we know what that rate of the reaction is, we can write a mathematical model of what's going on. And once we have a mathematical model of what's going on, we can put it in a computer. And so there's a set of steps that you're going to go through consistently in interpreting a diagram like that and turning it into a computer simulation. And some of these steps may seem, in a sense, very obvious, but they're obvious here because we're doing a very simple example. In more complex examples, it may not be so obvious how to go through these steps. So what we want to know is how the production and amount of C depends on the amounts of A and B. And the first thing we have to do is name these. Our molecular interaction diagram is talking about molecules, molecular species, that would correspond essentially to type names, what we call type names in CompuCell. But we're going to have a name for the concentration or the amount. And typically, notationally, we're going to use italics to represent amounts and the bare font to represent the species. The second thing is we need some kind of representation of what the speed of reaction is, and that typically is written over the arrow. And here we have A plus B goes to C at some velocity, V sub F. And then the last question is, what does that velocity of reaction depend on? And in fact, it depends on a lot of things. At the minimum, it better depend on the amount of A and B we have. But in any real system, it'll depend on the temperature, the pH, the pressure, maybe the magnetic field we've applied to it, and a bunch of other stuff. And so we're going to typically ignore all of those things and simply say that the reaction rates depend on the amounts. But there's no reason that that should be true in general. And depending on the situation that you're working in, you may need to worry about other things. In biology, normally animals regulate their body temperature, and so the temperature is pretty well confined. But if you're a Drosophila, maybe you're not temperature regulated, and the temperature might make a big difference. In the case of Dictyostelium discoideum, the reaction rates for certain key molecular species depend on the light intensity and the temperature, and that allows the organisms actually to move to higher temperature regions and also to move away from light. They're photophobic. So you have to know that. Okay. Another thing that we're going to do in general is we're going to assume that our molecular numbers are enough that we can talk about concentrations. But we have to remember that in reality, every molecular reaction happens on one molecule or one set of molecules. And very often in biology, the number of copies is very small. If we're talking about typical enzymes, we might have 10 copies in a cell. If we're talking about DNA, we have 1 copy in the cell. And so the idea that we're approximating 1 by a concentration is a little peculiar. And so one thing that one should be aware of when one does this kind of modeling is that the continuum hypotheses we're making about concentrations may or may not be appropriate. If it's okay, I could still use this. Okay? The other thing is that reactions are stochastic. And again, if the molecular, we're talking about molecular reactions with, say, oxygen, where there's a lot of it, then the approximation of a deterministic reaction is reasonable. If we're talking about the binding and unbinding of a transcription factor to DNA, and we typically are either on or off, and the net rate represents the typical fraction of time over which something is bound. And in that case, the continuum approximation actually may give us results that are not only quantitatively wrong, but qualitatively wrong as well. Again, in the time we have here, I can't go into all those details, but something to be aware of. And then the last thing that we need to worry about is that we need to assume that the concentration is roughly uniform over the volumes we're interested in. If you're a bacterium, even though that's a small volume, assuming bacteria are well stirred is not a great approximation. In eukaryotic cells, it's a worse approximation. And we can always go to these field models that we've shown you before if we need to do spatial variation. But computationally, dealing with fields is very expensive. And so if you can assume that things are, in fact, uniform over some volume, it helps you a lot. But all of these are very harsh assumptions. In fact, at some level, it's rather amazing that any of these models work at all. So, if we make the assumption that we can write the amounts of A, B, and C as concentrations, and we can assume that reactions are continuous in time and deterministic, and that we can ignore space, all of which are hard, then we could take our reaction A plus B goes to C. Its rate depends on the concentrations of A and B. And then that molecular reaction equation becomes 3 separate first-order ordinary differential equations that represent how the amounts of A, B, and C change in time. So A and B are disappearing and C is being created. So dA by dt is minus VF, dB by dt is minus VF, and dC by dt is VF. If we want to do anything more than that, we have to have some hypothesis of the form of the rate law. Okay. And I'll talk a little bit more about possible rate laws. But the simplest rate law that we're going to run into is called mass action. And you could think of mass action, well, there are chemical arguments for why mass action is reasonable. There are physics arguments for why mass action is reasonable. There's also a very simple mathematical argument for why mass action is reasonable, which is if I have no A, the rate of reaction better be 0, because I can't have a negative amount of A. And if I have no B, the rate of reaction better be 0. And the simplest functional form I can write that goes to 0 when A is 0 and B is 0 is A times B. And in fact, no matter what my functional form is, it has to have a term of that kind as the lowest order expansion, a Taylor expansion of the form. And so mass action says that the rate law, rate, is proportional to the amounts. And in particular, if I had 2A plus B goes to C, the amount would be, in the rate law, would be A squared. We can come back to that in a bit. So that's mass action. And so now, the assumption of mass action, I can write that dA by dt is some rate constant K times AB, same for B, and C is the reverse. Now, if I want to go further, I have to say at some initial time, whenever I'm going to start my simulation, typically we'll start at time 0, but there's no reason we have to do that. We have to say we have some initial amounts of A, B, and C, initial conditions. And those are typically written either A sub 0 or A of 0. Different people use different notations. Okay. And clearly, these are molecular amounts or concentrations. They have to stay positive. And so now we have a mathematical model, and we can implement it in principle in a computer simulation. And so now I'd like people to launch whatever you have. And again, it's critical that everyone have their computer out and do this. Because if you don't do this now, we won't be able to then go on and do the other things that we need to do. And if you're on a Mac and there's a problem running Tellurium, then you grab Andy, who's the local expert on getting things working. I'll show you the syntax. At the moment, you just need your editor running. Okay. You're going to find that Tellurium uses its own custom language called Antimony, just what you need, another language, and Python. The good news is you're already using Python in CompuCell, so just the way you had to learn essentially 2 languages, the Python CC3DML and Python, here you're going to have Antimony and Python. The good news, perhaps, compared to the CC3DML is that Antimony syntax is very, very simple. And the reason we're using this rather than Jim Sluka's favorite Copazi, which is another SPML editor, is that the syntax is so simple. Okay. So if you have, so how many people had Spider 2 and Tellurium on their machines? Okay. So what you'll see if you're running Spider 2 is that there'll be a left-hand window, which is an editor window, where you can type text and save it. So that's a little bit like Twit. And then there'll be a run button, which is a little bit like the run button in Player. And then there'll be a right-hand console window where you can type Python and do things live, and where things will display. If you're running in some other environment, it may look a little bit different. Okay. So when you use Tellurium, Tellurium actually puts your entire model into the form of a string and then executes the string. So what you'll see in a Tellurium model is a line that says import Tellurium, STE. In older versions, you had to import Roadrunner separately, but I believe that you don't have to do that. It's included with Tellurium now. And then you'll have a pair of lines that'll say something that looks like this. R equals TE dot load A, open parenthesis, and then 3 double quotation marks, and then a new line and 3 double quotation marks in the close parenthesis. And that somewhat awkward syntax of 3 double quotation marks is Python marking of a string with carriage returns. Normally, if you have a simple string and you put a carriage return in the middle of the string, that truncates the string. And so a triple quotation mark says that you can have carriage returns. So anything that's between these two here is this. And load A is a function defined in Antimony that says whatever is in that string is a program written in the Antimony language, and that's the thing you're going to run. Okay? Is everybody able to do this? I should say also that all of the demos that I want to talk about are available in the CompuCell website. They're in subfolders which may not be the most informatively named, but they're all there. Okay. So what I want to do now is together write the simplest possible model we could write, which is the chemical reaction A plus B goes to C with mass action kinetics. And effectively, once we could do that, we could do almost anything. Okay? So here is the code you need to type. So I would suggest that go into whatever editor you're using. You can skip the import roadrunner command because it's not required. It won't cause an error though. So you type the lines import Tellurium as TE, R equals TE dot load A, open parenthesis, triple quotes, and all of the coding that we're going to do is going to live between those triple quotes. That's the model specification. And again, you could think of that like the XML we've been using for CompuCell. Okay, so let's walk through this little code. The first line, or 2 lines, simply import Tellurium so that the functions available in that package are available to you. And we typically call it TE, something short. You could call it Tellurium. You could import Tellurium as Tellurium if you wanted to. Okay. The second thing we have is this pair of lines, R equals TE dot load A, triple quote, and this closing triple quote, close parenthesis. And that's saying that everything between those 2 lines is an Antimony specification. An Antimony specification is just a string. And so one thing that you will find, because it's just a string, is that if you make a syntax error in your string, execution will fail and it will not give you a diagnostic of where it failed. Because the string doesn't have line numbers. The string is just a string. Again, the good news is that Antimony syntax is so simple that generally you won't make syntax errors. And the names of things are up to you. In other words, we're calling this model R, but you could call it hello or my model or something else. All right? And now we're going to look at Antimony. And the reason I like Antimony is that it's exceedingly simple. So if I look at line 11 looks like the following. R1 colon A plus B arrow C semicolon K times A times B. Well, let's look at my chemical reaction. My chemical reaction is A plus B arrow C at rate K A times B. So what I've typed is R1 is optional. That's saying I've got a name for the reaction. I'm naming the reaction R1. If I left that out, it wouldn't make any difference, but if I have the name, I can refer to it later. And then I type A plus B arrow C, which is exactly what I have here. And then semicolon, which is the separator that they use in Antimony. And then the rate law, K times A times B. So in a sense, there's no more simple way I could translate what I see on the page in terms of my chemical reaction into computer code. Okay. And essentially everything you're going to do in antimony, with very few exceptions, will be typing lots of rate equations like this. You'll type A plus B goes to C at some rate. C plus D goes to E at some rate. A plus B goes to whatever at some rate, okay? The next thing I have to do is define my initial conditions. How much A, B, and C do I have at the beginning? So I start, say, with 10 units. I can define units if I want to, but to begin with, it's unitless, but I can imagine these are in moles. So I have 10 moles of A, 10 moles of B, and I say there's no C. And then I have to define the constant in my rate constant, my rate law, okay? And that's it. And now I have to run it. And the Tellurium has a couple of numerical integrators, but the one we'll typically use is something called simulate. And simulate says take whatever model was loaded in this TE load A and run it. And it runs it between time 0, first start time, stop time, and the third number is how many time slices to use. So delta T is time final minus time initial divided by the number of points. And if you make that number of points very large, the simulation will take longer. If you make that number of points too small, the simulation will crash because the integrators will diverge. Okay. And if you happen to be the one person who's using Spider, if you now hit run, it will run the simulation. It's not too bad compared to CompuCell syntax. The syntax is pretty simple. You can actually do an amazingly elaborate things with it, because you could build very complex models using these very simple ideas. I mean, the name, R1, as I say, this is optional. This is a name. So this names the chemical reaction. So if you don't have it here, it won't change anything. As a matter of good practice, it's not a bad idea if your equation was number 1 here, to name it so that you know this line corresponds to the equation in your paper. The other thing is that if you name it, the rate itself becomes available. And so if you want to know not only how much of the thing you have, but how much per time, how much of C is being created, R1 will contain the time derivative. And so it's actually a useful thing to have, but you don't need it. It's just a naming convention. There are a lot of things in antimony which come with SPML for specifying units, for specifying compartments, for specifying the names of things, which aren't absolutely required, but which help you make things readable. And so sometimes you'll see that I'll name reactions, sometimes I won't. It's not required. Okay. So I'd recommend saving this somewhere that you can get to it. And the question is, what happened? Did you run it? Did anything happen? No, should have run, but not shown you anything. And the reason it doesn't show you anything is that we didn't ask it to display anything. And so, sorry? So somebody's using a strange IDE that automatically plots results. That's interesting. So the variable result now contains the output of our simulation, but in most IDEs, result won't be plotted. On the other hand, we could now go into whatever your user interface is and just type the word result, and that will display the contents. Or you maybe put result parenthesis print close parenthesis. So why don't you try that? And if you do, what you should see is a big NumPy array. And the NumPy array has a structure. The first column is the time. The second column is the value of A. The third column is the value of B. And the fourth column is the value of C. And so if everybody make sure that that works. Okay. So there's a very good question. Suppose my chemical reaction were 2A plus B goes to C. Okay. If I write 2A plus B goes to C, it will automatically deduct 2 A's for every reaction. However, the rate law won't change. So what's called the stoichiometry is taken care of by this arrow diagram. That's the conservation of mass. But the rate law is whatever I type. So there isn't a flag that says use mass action, for example. You have to type the rate law yourself. Okay? One of the things that we could do is we've written this array is big. Suppose we only simulated for 10 time points instead of 1,000. So try that. The result equals r.simulate 0, 40, 10 instead of 1,000. Run it again.